Welcome back to Geology of the National Parks. This is Week 2, Topic 2. This lecture will cover a number of things: continental hotspots and Yellowstone National Park. Let's start out with a brief recap. Rocks are made of minerals. We got some rocks over here like granite, sandstone, and gneiss. They are composed of mineral crystals. Quartz, feldspars, and micas are all minerals that are sometimes present in these three different types of rocks. Every mineral has its own temperature at which it melts. Some of these are very, very high, like up to 1900 degrees Celsius, very, very hot. Other minerals melt as lower temperatures, as low as 575 degrees Celsius. Also recall that the mantle occupies most of the planet's volume and is made of ultramafic rock. That is rock that is comparatively extremely low in silica and enriched in iron, magnesium, calcium, and other trace elements. This rock can melt either by decompression melting, where hot mantle rock, remember it is solid rock though it is plastic, rises at somewhere like a mid-ocean ridge and melts as the pressure decreases and it comes closer to the surface. The other primary area where we get melting of mantle rock is at hot spot areas where, again, rising hot mantle material will lose pressure and either directly melt or cause melting in the overlying lithosphere. And this produces mafic magma, which contains slightly more silica and slightly less iron, magnesium, and calcium and other trace elements. And remember, mafic magma produces basaltic lava. And these are all igneous rocks. These are rocks that solidify from magma, which forms when rock in the Earth's interior melt. The magma rises through the Earth, it cools and solidifies to form a new rock, either on the surface as lava or in the interior of the Earth as intrusive rock, which we'll talk about shortly. We name or classify igneous rocks based on their chemistry, i.e. silica content, and how they cool. Let's start with the simplest one of these, obsidian or volcanic glass. Usually volcanic glass is felsic because it contains an extremely high silica content, and glass, as we know, is silica or quartz, SiO2. This is the same stuff that window glass is made of. Volcanic glass tends to be dark in color because it contains many trace elements and tiny microscopic mineral grains, but the bulk of it is glass. You do get mafic glass too, particularly in places where lava interacts with water, like this is obsidian glass sand from Hawaii, but over here we have lava flows from Central Oregon, Newberry National Volcanic Monument. This is an obsidian flow where a large rhyolitic, it's called felsic lava, flowed onto the surface and cooled quickly enough to turn into glass. Glass tends to be very dark like this. Some igneous rocks are composed of fragments. We call these pyroclastic rocks. Clast means piece or chunk, and clastic rocks are made of pieces of rocks, essentially. Most of these cool quickly enough that there isn't time to form mineral grains, and they are dominantly glassy, kind of like a microscopic glassy sponge. They're very frothy. Very small fragments of pyroclastic material are called ash. These are small shards of kind of frothy glass. You can see a microscope photo of 1 grain of volcanic ash up here. When they're first deposited on the ground, they tend to be quite powdery. You can see these hands are holding some ash as well. Very powdery, looks like sand. It's a little bit finer in texture, but it's very soft and powdery when it's first deposited, and you find pyroclastic rocks from explosive volcanic eruptions. Rocks made mostly of ash and to some degree other pyroclastic rocks, but mostly volcanic ash, are called tuff or ignimbrite. There are several tuff deposits in Yellowstone resulting from various eruptions of the Yellowstone volcano system. A section of one of those, the Lava Creek tuff, is shown on the right, with this yellow arrow here is pointing to a layer of almost pure ash. That's ash without any other stuff in it. It's just there's a very thin layer of very pure ash in this photograph, which you can see as a very light layer. Below is a sample of a tuff from California. called the Bishop Tuff, which is slightly smaller of a caldera system than the Yellowstone system, but it exists. It's only slightly older than Yellowstone. California has several very large supervolcanoes, and the Bishop Tuff comes from the youngest of those. It's very interesting, but you can see from these photographs it contains other pieces, other clasts of material. So this tuff, this ignimbrite, is not pure ash. It contains large blocks of other stuff. Tuffs can be felsic, intermediate, or mafic. Mafic tuffs tend to be rare and tend to form in places where you have water interacting with the basaltic lava. Down here on the lower right, we see two layers of tuff deposited by the Yellowstone volcano. The Lava Creek tuff and the Huckleberry Ridge tuff are the two most recent and largest of the eruptions from Yellowstone. But we'll talk about those more in depth shortly. Again, we name or classify igneous rocks based on not only their chemistry, but also how they cool. Glasses cool the fastest. Frothy-looking, medium-sized fragments coming out of volcanic eruptions look that way because they cooled from a very gas-rich magma. And these are called scoria, if mafic, seen here on the right, it's dark in color, or pumice, if felsic or intermediate, seen here, lighter color on the left. Scoria is produced during sort of fire fountains like we saw when we were discussing Hawaii, or pumice you can get during a pyroclastic flow, which we'll talk about in a later lecture, or any kind of high silica, high gas content volcanic eruption. Pumice will float on water because it is so gas-rich. It's basically a glassy sponge. It contains a lot of gas and it will usually float on water. But scoria is too dense. Not only the fact that it contains a fair bit of iron and magnesium and other metals because it's mafic, but it's also just tends to be a little bit more dense. And this is generally dark gray or black, but it can also be bright red. And this is the same sort of stuff that cinders, we talked about cinder cones, cinders are composed of scoria. So rocks that don't cool as quickly as glasses do, we have mineral grains present in the rock. These crystal grains either form in the magma underground, or they will form on the surface as your lava is cooling. These rocks are classified by their abundance of silica and whether they are fine-grained or coarse-grained, which shows us how fast or slow the magma or lava cooled. Where you have tiny microscopic crystals, your rock cooled very quickly. Where you have larger crystals, your magma cooled very, very slowly. Crystals grow over time, and the fact that you have large crystals in a rock means that you had a lot of time to grow crystals before your magma completely cooled. Mafic rocks, intermediate rocks, and felsic rocks all have their unique kind, their unique types of coarse-grained versus fine-grained, extrusive on the left versus intrusive on the right. So your fast-cooling, fine-grained rocks for a felsic rock would be something like a rhyolite. These tend to be pretty light in color, often kind of pinkish. An intermediate rock is something like an andesite, which tends to be sort of a light gray or a bluish color. And then at the bottom, your mafic rocks are going to be basalt. We have a lot of basalt here in the Northwest. It's very dark in color, generally very fine-grained as well. This slide shows the mineral abundances that you get in certain kinds of rocks. For felsic rocks on the right, you get a whole suite of minerals, including amphibole, biotite, muscovite, sodium-rich feldspar, quartz, potassium-rich feldspar, and your intrusive or plutonic or coarse-grained versions of a felsic rock is granite, and your extrusive, volcanic, fine-grained rock is something like a rhyolite. Your intermediate rocks, you still have amphibole, biotite, and muscovite, much more amphibole in an intermediate rock, a lot of plagioclase feldspar, a little bit of quartz, and a very small amount of potassium feldspar. Your intermediate would be something like a diorite, or a extrusive andesite. Diorite often gets confused for granite. They can look very similar, but diorites tend to have, again, a lot more plagioclase feldspar and a lot more amphibole than a felsic rock would. We already talked about basalt being the fine-grained extrusive version of a mafic rock. The main minerals are calcium-rich feldspar, pyroxene, amphibole, and sometimes olivine. Olivine is actually very important Olivine is actually very important in basalt and can tell us a lot about the chemistry of the magma that produced the basaltic melt. Its coarse-grained, intrusive version that cooled underground is called gabbro, and it tends to be very dark. And then on the ultramafic side of the spectrum, we have peridotite, that green rock that makes up most of the mantle. And it's very, very rare, but the fine-grained extrusive version of ultramafic lava would be komatiite. Very, very rare. We don't see this in the US very often, and I'm not going to spend much time on it. This is Bowen's reaction series, as you may recall from the last lecture. Just as a review, mafic magmas have to be hotter than the melting temperature of felsic rock, because your low-temperature magmas are full of things like potassium feldspar, muscovite mica, and quartz, whereas your high temperatures are required to melt those minerals and create olivine and pyroxene, and melt everything else and just leave behind the heavier iron and magnesium-rich minerals. Felsic rocks melt at low temperatures. Mafic magmas cool and solidify at temperatures much higher than the melting temperatures of felsic rocks. So we spent the last lecture talking about what happens when a mantle plume or a hot spot reaches the oceanic crust. Generally, it sort of punches right through the oceanic crust, which is thin and already composed of mafic rock, and you get mafic volcanic centers in the middle of the ocean, oftentimes. And this is a result of the mafic melt going through mafic rock and erupting relatively quickly without being modified or stored or being subjected to all sorts of complicated chemistry that tends to exist in magmatic systems. As we've already discussed, the lithosphere is much thicker and made of different stuff than our oceanic lithosphere or oceanic crust is made of. So when you get mafic magma forming inside of and beneath the continental lithosphere, it goes through a couple of different phases. It has to rise through the ultramafic lithospheric mantle portion without melting the surrounding rock, without getting contaminated by the surrounding rock. Oftentimes it then stops and pools sort of at the base of the continental crust. There's a compositional boundary at the base of the continental crust called the MOHO, which is short for Mohorovic discontinuity, but you don't need to know that. The MOHO is the base of the crust and the top of the mantle, although it's all part of the lithosphere. When your mafic magma pools at the base of the crust, it starts to heat those crustal rocks to temperatures above their melting point. Your felsic rocks that compose the crusts melt, remember, at lower temperatures than your mafic rocks do. So your hot mafic melt is pooled at the base of the crust, and it causes melting in the lower crust. And this melting creates felsic magmas, which rises up through the crust and feeds different kinds of volcanic systems. Mafic melt can rise through the crust, but it tends to rise really quickly and not be contaminated again by the surrounding rocks. And if it does get contaminated, then it turns into intermediate or felsic melt. And basaltic melt feeds shield volcanoes, which are short and stubby. Felsic magmas feed, among other things, tall stratovolcanoes, which are pointy and triangular, but also the large caldera systems, such as Yellowstone, which we'll talk about in this lecture. The primary difference between oceanic hotspots and continental hotspots is the chemistry of the magma and what happens in the crust as this basaltic magma rises through it. You get to very similar things in both, in that you have a trail of older volcanoes in the direction of the plate motion, leading away from the hotspot. On the left, you have your oceanic hotspot leaving a trail of volcanic islands. On the continental hotspot, you have a trail of solidified magma chambers extending away from the head of your mantle plume. Both continental and oceanic hotspots have eruptions of mafic magma, forming partial melting of the mantle by decompression melting. That decompression melting does form basalt flows. We have basalt flows on continental hotspots, but they coexist at the same time as highly felsic rhyolitic volcanism, at the same place and sometimes the same time. Continental hotspots have large eruptions of rhyolite. Rhyolite usually composes the largest volume of material erupted from continental hotspot centers. And this is a felsic rock, again, formed by heat-induced melting of crustal rocks. But the two magmas generally stay distinct. They tend not to mix very much. So this gives us something called bimodal volcanism, where we have both mafic and felsic rocks erupting at the same place and often the same time. Let's start with Yellowstone National Park. It is the first thing in the United States that is called a national park. It was created by Congress and signed into law by President Ulysses S. Grant on March 1st, 1872. So Yellowstone's been around for a long time, 153, almost 54 years at this point. So it has a lot of great human history, fascinating human history, but the geology is just as interesting, and it's really what we're here to talk about. So let me get into that. Let's start by talking about the Yellowstone hotspot, the actual mantle plume that is feeding volcanism in Yellowstone and some of the surrounding region. So using the velocity of seismic waves traveling through the Earth's crust, we can actually image the relative hardness of rocks deep in the subsurface. Here in the lower left, we're looking at a cross-section, three-dimensional view of beneath the Yellowstone area. All of this red stuff is what's called a low velocity zone, where seismic waves travel very slowly through it. And that indicates that that rock is A, very hot, and B, contains a proportion of melt. And seismic waves don't travel through liquid. So the slower the seismic waves travel through, that tells you how much liquid you have. So this low velocity zone shows us the actual hot spot rising through the lithosphere and upper mantle beneath Yellowstone, and that's really cool. And remember, there's two main theories for how hotspots form. One theory, my personal favorite one, suggests that hotspots are coming up from mantle plumes rising from the outside of the inner core, rising all the way up through the lower mantle and the upper mantle, and then eventually feeding volcanism in the crust. The other model suggests that there are distinct convection cells feeding an upper portion of a hotspot and a lower portion of a hotspot that do not mix. But the end result is the same, where we have hotspot volcanism feeding melting in the upper mantle and the lower lithosphere and the lower crust, feeding volcanoes on the surface and creating these large, complex systems that can form enormous volcanoes. The Yellowstone hotspot feeds bimodal volcanism, and this is characteristic of a continental hotspot. Initially, when the hotspot first reaches the base of the crust, it's sort of a big mushroom cloud shape, and it balloons out along the bottom of the crust. And this feeds widespread flood basalt volcanism. Our new featured word for this week is large igneous province, and I'll talk about that in a couple of slides. So it's thought that large igneous provinces, such as flood basalts, are part of the initiation, the first part of the hotspot reaching the continental crust's base. Following your large igneous province, you get felsic volcanism, eruptions of rhyolites, the creation of large caldera systems, and abundant light-colored volcanic rock. Following your large rhyolitic eruptions, you will get smaller, late-stage eruptions of basalt in your caldera and in the surrounding region after your area moves off of the head of your hotspot plume. We see bimodal volcanism, which is the eruption of felsic magma, followed by later eruption of mafic magma, everywhere we see upwelling mantle material, causing decompression melting beneath continental crust. Some of this exists in the Basin Range, for example, but that's a little bit beyond the scope of this course, unfortunately. Here are the world's large igneous provinces. They come in two primary flavors: continental, which exists on the continents, and oceanic, which exists in the oceans. Iceland is actually a large igneous province, but it has two phases, one going back to about 60 million years ago, and the other being active currently to about 56 million years ago. So there is a large hotspot beneath Iceland, in addition to it being located on top of the mid-Atlantic ridge. But the one we're mostly interested in is the Columbia River flood basalts. The Columbia River large igneous province, which was active from, this map's a little outdated, it was active from about 17.5 million years ago to about 10 million years ago. Let's talk a bit about that now. The Columbia River basalt group started erupting about 17.5 million years ago down here, all the way in southeast Oregon around the Steens Mountains area, where there is a dike swarm, a large concentration of these planar igneous intrusions. Remember, a dike is a planar igneous intrusion that feeds a fissure volcanoes. So we have had hundreds of these fissures feeding hundreds of lava flows that blanketed almost the entire Pacific Northwest, extending from northern Nevada, clear up through the western edge of Idaho, up through most of Washington, all the way out across northern Oregon and down the ancient Columbia River into the Pacific Ocean. Many of the rocky headlands along the Oregon coast are actually made of Columbia River basalt. So there are actually thousands of these dikes that fed dozens and dozens of lava flows that poured out thousands of cubic miles of basaltic lava that flowed out across the landscape and basically completely leveled the landscape and buried the old landscape underneath hundreds and thousands of feet of lava. If you ever travel in the Columbia River Gorge or eastward along I-84, most of the rocks you're seeing are Columbia River basalts derived from these eruptions. On the left, I've got a picture of Lateral Falls, which is a waterfall that pours over 3 of the lava flows making up the one of the units of the Columbia River basalt called the Grand Ronde basalt. So this is just 3 of several dozen lava flows that have stacked up and formed the Columbia River basalt group. And the Columbia River basalts are widely accepted to be that first stage of the Yellowstone hotspot when it reached the base of the crust. When that mantle plume, large mushroom cloud-shaped body of hot rock coming up through the mantle, reached the base of the crust, caused mafic magma to melt and form. That then rose up and opened up thousands of fissures in Oregon, Idaho, and Washington that poured out thousands of cubic miles of basaltic lava that completely buried the landscape and created a brand new landscape composed entirely of basaltic lava. It is widely accepted that the Yellowstone hotspot has existed in its current location for about 16.5 million years, and that it is responsible for the creation of about a half a dozen large caldera systems across the Pacific Northwest. Remember, a caldera is a collapsed area that forms after rapid removal of magma, usually accompanying a large explosive eruption. Here's the life cycle of a large caldera. First, your magma chamber swells up and forms a domed area. It arches up and fractures your overlying rocks, and you get these sort of concentric ring fractures forming around the top of your caldera, the top and edges of what will be your caldera. Fractures eventually tap directly into your magma chamber. In this case, we've got a very gas-rich rhyolite magma chamber, and that releases some of the pressure, giving you volcanic eruptions and the upward migration of that magma toward your eruption sources. And this fuels enormous volcanic eruptions of rhyolite ash that will cover the landscape, cover thousands and thousands of square miles, and can be tens, dozens, hundreds of feet thick. And these vast ash flows are the primary product of caldera eruptions. After your eruption ends, the roof of your magma chamber collapses downward because it no longer has the pressure either of that rising magma or the supporting force of that rising magma, and it has to collapse down and fill the void left behind by the escaping magma. Later on, basaltic magma will rise through the magma chamber and produce basaltic lava flows on the floor of your caldera. Because the rhyolitic melt is isolated in the top part of your magma chamber, but the lower part of your magma chamber is still basaltic mafic melt. So as the top part of your magma chamber evacuates, all your rhyolite escapes, and you're left with basalt rising up through those leftover cracks and covering much of the caldera floor. So let's talk about the scale between mafic caldera systems like Kilauea, seen up here in the upper left, Crater Lake, which is sort of an intermediate caldera, and then Yellowstone caldera. Kilauea is a couple of miles across, it's about a mile wide, and it's here on Yellowstone National Park. This is to scale. Crater Lake actually began as a rhyolitic felsic eruption, but then as it evacuated its magma chamber as that volcano erupted, and we'll talk about this more in detail later on in this course, it collapsed down, and then intermediate and mafic magma started coming out and erupting. So Crater Lake is about 6 miles across. It's here to scale on Yellowstone National Park. And then the caldera rim of Yellowstone, which is a rhyolitic felsic caldera system, is here. It is, let's see, about 40 miles across. So it's a much larger volcanic system, a much larger caldera, A lot of people will call this a supervolcano just because of how big and large it is. That is not a geologically defined term. There is no scientific thing as a supervolcano, but it is a good colloquial term for understanding just how much bigger caldera systems can be than your typical volcano that we generally think about. And the Yellowstone calderas are just the most recent ones of a series of calderas that extend all the way across Idaho and into the border of Oregon and Nevada. The oldest one of these, called the McDermott caldera, first started about 16 to 15 million years ago, and it erupted for a while. Then it cooled off, and the plate kept moving, and so we got the Owyhee-Humboldt caldera 13.8 to 12 million years ago. And then it cooled off, and the plate kept moving, so then a few dozen miles to the east we get another caldera. This one, the Bruno-Jarbidge caldera, was active about 12.5 to 11.3 million years ago. The hotspot erupted in that place at that time, and it was a very large eruption. All the way across into Nebraska, we had over a foot of ash deposited. And that's from Idaho to Nebraska. And then traces of that eruption are found all across the eastern United States. The eastern 2/3 really of the US is covered by ash from that eruption. And in Nebraska, where we had, again, about a foot of ash fall, ancient camels, horses, and rhinos were killed by the ash from this eruption, both by starvation following the death and burial of all of the plant life that was there, but also just because the atmosphere became unbreathable. All of these animals died during this volcanic eruption. And they were preserved by that volcanic ash and are now being studied. It's a very important paleontological site today. There are 4 other large caldera systems between Bruno-Jarbidge and Yellowstone. Yellowstone itself has 3, which we'll talk about now. The oldest caldera at Yellowstone is the Huckleberry Ridge caldera, and it occupies this lightest purple area on the right image and this lightest yellow area on the left image, and that's about 2.1 million years ago. It is the largest of the eruptions in modern-day Yellowstone. It erupted about 2.1 to 2.2 million years ago, and it erupted 2,500 cubic kilometers of ash. That's an insane amount. That's a very, very large volcanic eruption. The second caldera in Yellowstone, the Island Park caldera, which is a little bit to the west of the modern boundary of Yellowstone National Park, it was a little bit smaller. It erupted 1.2 to 1.3 million years ago, and it erupted about 280 cubic kilometers of ash. So that's about 10% the size of Huckleberry Ridge. About 630,000 years ago was the Lava Creek caldera. That is the youngest and most recent caldera at Yellowstone. It erupted about 1,000 cubic kilometers of ash during its eruption. This here says 640,000. It's 638,000 is the date years ago for that eruption. So in cubic miles, that first caldera was about 600 cubic miles of ash. The Island Park caldera, about 67 cubic miles. And then the Lava Creek caldera, the third one, about 240 cubic miles of ash was erupted. This is a topographic map showing what Yellowstone looks like in the modern day. It's a sort of a high plateau on the western slope of the Rocky Mountains. The Absaroka Range is a sub-range of the Rocky Mountains. The average elevation of this plateau is about 7,500 to 8,000 feet, and it has mountains on the north rim, mountains on the south rim, mountains on the east rim, but then the west rim is what's called the Pitchstone Plateau. It is mostly made of lava flows. And these lava flows erupted after the primary eruption that created the Lava Creek caldera 638,000 years ago. There are other later lava flows covering the caldera floor. The youngest one of those is about 70,000 years old. So the caldera rim is not a topographic feature everywhere. There's really only one spot where you can see the edge of the caldera, and it's right here on the northwest rim. This is the caldera rim. This is all composed of Lava Creek tuff, Lava Creek ignimbrite, ash from that eruption. And then the younger lava flows are visible here within the caldera floor. So what about Yellowstone's next eruption? You hear a lot about that from sensationalist and dubious credibility quote-unquote geology news sources, lots of media panic about the Yellowstone every few years. Its next eruption is likely to be on a similar scale to its previous ones, its next caldera-forming eruption, that is. But it's important to remember, volcanic systems are not alarm clocks. They operate on their own timelines with margins of errors of thousands of years. So just for example, the intervals between the eruptions look fairly regularly spaced, about 600,000 years apart. The rock ages have error, though, of a few thousand years. The most recent eruption was 638,000 years ago. So does that mean we're overdue? Not really. I mean, that's 600,000 years plus or minus 100,000 years, because there is variation. These are not perfect, regularly operating systems. They exist in the natural world, where there are other factors contributing to the mixture of magma, the production of magma, the behavior of magma as it's stored within the crust, all of those of which have to align in order to fuel a large eruption. We are not close to an eruption at Yellowstone. Current estimates put the magma chamber at only 5 to 15% liquid, the rest of it being solid crystals. So again, the magma chamber beneath Yellowstone is mostly solid, only 5 to 15% liquid. It is thought that we need at least 50% liquid needed for an eruption, so we need a lot more magma to be produced, and for that magma to flow up through the crust and fill up the magma chamber before we get another caldera-forming eruption at Yellowstone. That is likely to be hundreds of thousands of years in the future from now. So what are the most likely volcanic events in the near future at Yellowstone? Are we looking at a caldera eruption? Nope. We would be preceded by major earthquakes and volcanic eruptions for thousands of years before a major caldera eruption at Yellowstone. Would we see lava flows? Maybe. The last one occurred 70,000 years ago, but there is no current indication of magma shallow enough for a lava flow eruption to occur anywhere in Yellowstone as of the time of this recording. Hydrothermal explosions, that is the interaction between magma or lava and water, yes. These are the most likely things to happen in any given year at Yellowstone, with about a 1% chance every year of occurring, according to the U.S. Geological Survey's Yellowstone Volcano Observatory. These hydrothermal explosions are driven by superheated groundwater flashing to steam. Also, clogged hot spring systems can explode, and that happens about every year. The most recent of those happened in a place called the Biscuit Basin in 2024, and again this year in 2020, well, it happened in 2025. Let's talk a little bit about these hydrothermal explosions, some of which can be quite large. There's a circular crater up here. That's an old hydrothermal explosion crater about a half a mile across. But interestingly, on Lake Yellowstone's western edge, there's a place called Mary's Bay, and it's this large oval about a mile and a half across. It's possibly the largest hydrothermal explosion site in the world. It created a large hydrothermal volcanic eruption and explosion from the likely injection of shallow magma reaching near the surface, interacting with the water of Yellowstone Lake. That water then flashed into steam, carving out a huge crater and creating a large steam-driven explosion. On a smaller and more frequent scale, we get these hot spring eruptions. This one occurred in 2024 at Biscuit Basin. This eruption plume is several hundred feet tall. You can barely see the white dots down here, and those are people running away from this massive explosion. The underground plumbing system of hot geothermal water that's feeding the hot springs became clogged, and all of the pressure built up beneath that clog and then released all at once in this massive explosion. And that leads us very nicely into the many geothermal features we have in Yellowstone. Yellowstone contains over 10,000 thermal features. It is the highest concentration of geysers and other geothermal features anywhere on Earth. It can be found in Yellowstone National Park. And there are 4 different types. Geysers, the most famous ones, are intermittent hot springs that erupt fountains of boiling water. Some of these erupt fairly regularly, some of these erupt unpredictably, and sort of at random. Hot springs are just pools of superheated water that bubbles up to the surface and makes a nice big pool. Fumaroles are also pretty common. They are just steam and gas vents. They don't erupt, they just hiss steam all day long. And then mud pots are my favorite geothermal feature, where superheated hot water picks up sediment and mud and makes this sort of boiling puddle powered by steam and escaping volcanic gases. There are plumbing systems beneath each of these different types of geothermal features, and it's the nature of those plumbing systems that tells you what kind of geothermal system you're going to have. A geyser requires a sort of constricted nozzle opening at the surface, and then beneath that it needs large places for bubbles and boiling water and steam to accumulate, large chambers underground, and complicated snaking passageways for groundwater to rise through. And it's these bubble traps where pressure gets built up, and eventually that pressure overflows and your geyser erupts. Hot springs, on the other hand, have a much straighter shot of superheated groundwater rising through the glacial deposited gravels that cover most of the floor of the Yellowstone caldera. That hot spring water just rises through and slowly bubbles away in a nice, calm, and very nice looking pool. If you were to lower yourself into one of these hot spring pools, you would be badly, badly burned. But I'll talk about that in a second. Fumaroles, on the other hand, generally don't have much water. It's mostly steam, so they're boiling at a point somewhere deep under the surface rather than near the surface, and that just produces an continuous eruption production of steam and other volcanic gases. In most of the geyser basins in Yellowstone, this comes from cooling lava flows. Snowmelt rainwater will percolate through the gravels and upper portion of lava flows and volcanic rocks of the caldera floor, and then it will percolate into those cooling lava flows and the superheated ground, which is kept warm by the magma chamber of Yellowstone, which is only about 3 miles below the surface. And then that water will rise as it gets heated and feed the different geothermal systems like geysers, hot springs, and fumaroles. This is a cross-section of the system beneath Old Faithful, the most famous geyser in the world, probably. About 62% of the world's geysers are in Yellowstone National Park. Other locales are in New Zealand. California has actually a lot of geysers in it in a few places. Iceland has a lot. Indonesia has a lot in a few places. The word geyser actually comes from the Icelandic word geysir. There is a geysir. A friend of mine went there. It's in Iceland. You can go see it. It is the what's called the holotype of the geyser. It is the place where the term geyser originated and where sort of it's defined from. Geysers always require a very high ground temperature. They require very shallow groundwater and high porosity, or a storage chamber for steam and boiling water to accumulate. The bubbles from these volcanic gases escaping from cooling rhyolite flows and the underground magma chamber need to be trapped until that boiling overflows the storage area and it erupts. Old Faithful's system just happens to refill very quickly and very predictably. It is not particularly unique among geysers for being either highly predictable or highly regular. There are some that erupt continuously. Some geysers erupt every 5 minutes. Some geysers are completely unpredictable, like Steamboat Geyser, the tallest geyser in the world, which will occasionally erupt over 400 feet into the air. That geyser is completely unpredictable, and it erupts sort of whenever it wants. Fairly regularly sometimes, and sometimes it will go a decade without erupting. It all depends on the plumbing system beneath that geyser. And again, hot springs are very scenic, they're very beautiful, they're very alluring. Many hot springs get their colors from thermophile algae and bacteria. That is algae and bacteria that loves to live in extremely high temperatures. Hot springs generally have a range of colors, and the temperature of the water correlates with the color. Blue, or in this case dark green, is generally not containing algae because it is too hot. Yellow-orange, it is still very, very hot, but it's a little bit cooler, so that's where you get some of your algae and bacteria starting to form. But the orange is where the thickest layers of algae and bacteria are, so that is the coolest temperatures, but they are still hot enough to scald you. Because we're at high altitude, water boils at only about 190 degrees Fahrenheit. So this hot spring only needs to be 189 degrees Fahrenheit for it to not boil and become a fumarole or a geyser. So the hot water rising into this hot spring, this is Morning Glory Pool in the lower geyser basin where Old Faithful is, could still be 189 degrees Fahrenheit. So if you were to jump into this hot spring, you would die immediately. And roughly every year, some tourist will try to get into a hot spring and they will be immediately scalded to death. This water is also highly acidic, and so their remains are usually considered not recoverable and dissolve away in the superheated, super acidic hot spring waters of Yellowstone National Park. And that's all for this lecture. I'll see you next week.